Okay, here we are, a beautiful afternoon, and we'd like to talk a little bit about rules of exponents. Our sort of mathematical objectives for this video and this assignment are to solidify the intuition behind the rules of integer exponents, and then explain, remember integers are whole numbers, and then explain why the rules of exponents are valid in our own minds. We want to be able to explain that. And so I think the goal here is to spend some time really digging into why these rules work. I think parts of this could feel tedious. Definitely spent a good amount of time constructing this, so hopefully you'll spend a little bit of time working through it as well. But I think it's worth it to own these rules so that you understand them and then you can use them, right? We got to understand the intuition behind something that's going to allow us to do things much more quickly, so that we can do that with confidence and without making as many mistakes. Although mistakes are okay, we just want to recognize why we made those mistakes and what we can learn from them, of course. But before we do that, we might just ask the question, why exponents, why exponentiation at all? And so I think mathematicians are after efficiency. I think a good question that mathematicians ask are, how can we make this more efficient? How can we make this easier for ourselves? Hopefully, as along with that comes along the question, how can we make our world more equitable? So hopefully those two questions go hand in hand. And so exponents make multiplication more efficient, right? Instead of doing 2 times 2 times 2, we can just do 2 cubed. Boom, we're done. So it's an efficiency piece for sure, but that's not really enough for me. And so I would like to suggest that studying exponents and understanding exponentiation is so that we can really understand things in the world where how quickly the thing grows depends on how much of it there is. And that's going to lead into a whole discussion of exponential functions, right, which is a whole nother type of functions in addition to quadratic and linear and other types of functions. And so I'll just use one example that is very, very real to all of us right now, and that is the COVID-19 pandemic. And that is modeled by sort of an exponential function. Actually, it's called a logistic function, but they're similar in many ways. And it makes sense because the more people are sick, the more quickly the disease spreads. And so that's why things like social distancing, making sure you stay 6 feet away from other folks, wearing your mask, washing your hands many times per day, especially when you're coming on campus. All these things are very, very important because as soon as you get sick, not only do we have another person sick, which is a tragedy, but we also have more people getting sick faster. So we've got something where how quickly it grows also depends on the number of people who have it. That would be like if you paid a cell phone bill and they're like, every additional text that you send increases the amount that we're going to charge you. Well, if that were the case, you would probably stop texting this much, or you'd spend a lot of money. So exponential functions are really interesting, and they model a lot of things in the world, including something that's very real to us right now, COVID-19. But this is going to feel a little bit different from COVID-19, or maybe it will feel worse because it'll be so tedious, I'm not sure. But anyways, hopefully that gives you a little bit of justification for why we're even doing this. Okay, so now we're actually going to jump in now that you've heard my little monologue. Or maybe you skipped it, Who's to know, really? So here's a definition. Exponentiation is repeated multiplication or division, we'll talk about that more later, of the number 1 by the base. Now we usually say exponentiation, like 2 cubed is multiplying 2 by itself 3 times. Well, it's actually multiplying 1 by 2 3 times. And it's not that big of a deal, except for it will help us understand division and negative exponents and some other things if we remember that exponentiation is actually repeated multiplication of the number 1 by the base. So here we go with number 1. 2 cubed is 1 times 2 times 2 times 2, which is 8. Now that is the same as 2 times 2 times 2. but I like to put the 1 because it's helpful later on. -3 squared, I'm squaring the whole -3 there. And so that should be 1 times -3 times -3, which is 9. 5 cubed, that should be 1 times 5 times 5 times 5, and that is 125. And I will let you do -1 cubed. Now down here, we'll scroll down and we'll just go backwards. Okay, so we're just going to go backwards here. 1 times 3 times 3 times 3 times 3 is 3 to the 4th because we're multiplying 1 by 3 4 times. 1 times 4, 4, 4, 4, 4, that is 5 fours. So that should be 4 to the 5th. We're multiplying 4 by 1 5 times. And of course, 1 times -5 3 times should be -5 in parentheses. Make sure it's in parentheses. Cubed. If we want to cube the negative, which we do because we've got the negative, 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 that needs to be in parentheses. Okay, so that's just reminding you what exponentiation even is. Okay, scrolling down here to number 3, it says, write out the full meaning and simplification of the following expressions, then write as a single power. So you can see we've got here for a -2 squared times -2 cubed. So that should be 1 times -2 times -2. That's -2 squared. Then 1 times -2 times -2 times -2, that's -2 cubed. And if we multiply all those things, we have 1, 2, 3, 4, 5 negatives, still going to be negative. And 2 times 2 times 2 times 2 times 2 is 32. That's -32. And if we write it as a single power of -2, that's -2 to the 5th, right? Because there's 1, 2, 3, 4, 5 -2's being multiplied by 1. Okay, let's do the same for B, and then I'll let you do C on your own. So 3 squared, that's 1 times 3 times 3. It's okay if you just write 3 times 3, but it's actually 1 times 3 times 3. Then we have 1 times 3 times 3 times 3 times 3. That is what 3 to the 4th means. And I believe if you multiply this out on your calculator, you will get 729. I do not have that memorized, but I know that's a power of 3, so it seems right. And now I'm going to write it as a single power of 3. So how many 3's am I multiplying by 1? 1, 2, 3, 4, 5, 6. That's 3 to the 6th. Now what we want to do is start recognizing the pattern. Oh, -2 squared, -2 cubed. That became -2 to the 5th. -2 to the 5th, -2 squared, -2 cubed. Ah, 2 plus 3 is 5. Interesting. Then we had 3 squared times 3 to the 4th. Okay, that ended up being 3 to the 6th. Ah, 6. Ah, 2 plus 4 is 6. Interesting. Okay, so we're starting to recognize that pattern there. All right, I'm going to let you do C, and I'm just going to go ahead and scroll down here. Okay, we come on to number 4. Based on your work in number 3, rewrite the following as a single power of a base. So hopefully you noticed that when you multiply two expressions with the same base and they're both raised to some power, you can just add those powers. So x squared times x to the 5th would just be x to the 7th. A cubed times a to the 6th, that would be a to the 3 plus 6. And that is just a to the 9, right? A cubed means multiply 1 by a 3 times. Then we multiply an additional 6 times for a to the 6, so that's 9 total. Okay, most common mistake would be to say that this is a to the 18th. No, it's not. You do not multiply those exponents, you add them. If you write this out, it will make sense because you'll have a times a times a, then you'll have a times a times a times a times a times a. So you've got 1 times 9 a's, that's a to the 9th, not a to the 18th. A to the 12th times a to the 17th, you're going to figure that out. And of course, I'll just call this the red rule. A to the m times a to the n, you add the exponents, you get a to the m plus n. Okay, hopefully that makes sense. You can ponder a little bit, right? I've spent hours pondering this, believe it or not. So you may want to do some pondering of your own. Okay, we're going to clear that. We're going to scroll down. Okay, now we develop the next rule, the orange rule. Write out the full meaning and simplification of the following expressions, then write as a single power of the base. The first is completed for you as an example. We've got 2 squared cubed. We said 2 squared is, or rather 2 squared cubed is 1 times 2 squared times 2 squared times 2 squared, right? We're cubing the 2 squared, so we're writing the 2 squared out 3 times. But 2 squared is 2 times 2, so we get 1 times 2 times 2 times 2 times 2 times 2 times 2, that's 2 to the 6th. Okay, notice the relationship between 2 and 3, those exponents, and 6. Shall we try B? I bet about 4 of you are like, no, Alvin, let's not. Let's do something else. Well, too bad, because I can't actually hear you, so I'm going to go ahead with it. Why not? Okay, 3 cubed squared. That is, let's see here, 1 times 3 cubed times 3 cubed, right? Because I'm squaring the 3 cubed. And then that should be 1 times 3 times 3 times 3 times 3 times 3 times 3. That's 6 threes. That should be 3 to the 6th power. Again, notice that if I multiply those two exponents, 3 and 2, I end up with 6. Okay, C you can do on your own. You can check the key. Based on your work in number 5, rewrite the following as a single power of the base. First, to complete it for you. X squared cubed is x to the 6th. We just multiply these two things. A to the 4th, all raised to the 4th power. That'd be a to the 4th times a to the 4th times a to the 4th times a to the 4th. And a to the 4th is a times a times a times a. And then a times a times a to blah, 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 blah. There are 16 a's being multiplied by 1 here. This is a to the 4 times 4, which is a to the 16th. And finally, down here, we should have b to the 21st power. So you'll notice that we're multiplying the exponents when we have a power raised to a power. That is different than up here when we were multiplying two bases that are the same, and then we added the exponents. Here we have power to a power. So the orange rule, a to the m to the n, again, you may need to ponder this a little bit, that's okay, is a to the mn, a to the m times n. Okay, so that's a little bit different because now we have a power to a power. We multiply the exponents. Okay. So for this next one, I am not going to do the whole thing, but I'm going to give you some hints. It says, come up with specific values for a, b, and n to show that the yellow rule is true. Okay, so here's what I would suggest you do. First of all, find some values for a, b, and n. Okay, it doesn't really matter what you pick. Pick some integers. Pick some positive integers. 2, 3, 4, 5, maybe even 1. Delicious Kenyan coffee. And just pick them. Hopefully you picked them already. I'm not going to pick them for you. Okay, so hopefully you picked some values, blah, 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 blah. Then I would suggest that you just maybe keep this on one side, a, b to the n. Plug in all your stuff here, equals, plug in your stuff. And over here, keep a to the n times b to the n. Plug in your stuff, and then just simplify on both sides. Simplify, and hopefully these, by the time you're done simplifying, they will be equal. So that would be my suggestion. Just pick some things, pick some numbers, plug them in, simplify, and hopefully that's the same. You can check the key if you want to, but try and choose some different numbers, because then that gives us more confidence that this thing is actually true. Okay, but what does it say? It says you've got two numbers that are multiplied by themselves, raised to a power. You can just raise each one of them to a power. Makes sense that this should work because exponentiation abbreviates multiplication. So multiplication and exponents are friends. Multiplication and exponents are friends. Addition and exponents, not quite as much. Worry a little bit more when you've got exponents and addition. Then you got to do a little bit more work. But with multiplication exponents, oh, they're very close relatives. They know each other very well. Okay, that's cool. Now we're going to scroll down to 8. Follow a very similar process, as to you did to number 7. Develop the green rule, which says if you've got a quotient, a fraction, you raise it to a power, you can just raise the top to the power and the bottom to the power. I'll just let you know that makes really a lot of good sense, because if you've got 2/3 and you square it, what should that mean? That should mean 1 times 2/3 times 2/3, right? That's what an exponent means. It means multiply 1 by the base. The base in this case is 2/3, 2 times. Great. But that's the same as 1 times 2 times 2 divided by 3 times 3. That's still going to give you 4/9 either way. So it's the same thing. So it doesn't really matter. Anyways, come up with a similar process for the one above, and you can show that. Here's a quote from one of my roommates. Anything that's a power of 2 is literally super useful. Computer scientist right here. Did you know that 20 questions covers about 1 million possible items? Because 2 to the 20th is roughly 1 million. Boom. Interesting. So if you ask 20 questions, you should be able to distinguish between over 1 million items. If it's outside of the million, you may need more questions. But an additional question will take you well over 2 million. So, and then you could get up to 4 million and, it gets pretty big pretty fast. And that is something we want to understand about exponents. They get large very quickly because the rate of growth depends on the number of items. We're going to complete this table. Few cells have been completed for you. You will need to think carefully about the patterns you see. Yes, you will. So we've got some powers of 2, which are literally super useful, according to my roommate who, codes and teaches computer science. So let's assume that she's right. 2 to the 5th, that's 2 times 2 times 2 times 2 times 2 times 1, which is 32. Then we've got 16. Of course, 2 cubed is a solid, let's see here, that is a solid 8, definitely. This has got to be 8. This is 4. This is 2. And what we kind of want to notice is when you go from 32 to 16, you divide by 2. When you go from 16 to 8, you divide by 2. When you go from 8 to 4, you divide by 2. When you go from 4 to 2, you divide by 2. So we want this pattern to follow because we've got 5, 4, 3, 2, 1 as our exponents. But we want the pattern to continue. So we need to divide by 2. And so 2 divided by 2 is 1. 2 to the 0th power is 1. And remember, 2 to the 0th means multiply 1 by 2 0 times, meaning it would just be 1. If you multiply 1 by 2 no times, you just have 1. Continue the pattern. Oh dear, -1. Ooh, negative exponents. Yikes. Negative exponents. Let's divide by 2 again. 1 divided by 2 is 1/2. Let's divide by 2 again. 1/2 divided by 2 is 1/4. Let's divide by 2 again. You get 1/8. So friends, negative exponents mean divide. 2 to the -1 means 1 divided by 2 one time. And 2 to the -2 means 1 divided by 2 twice. Okay, so the break-even point is right here. 2 to the 0 is just 1. Now, if you increase the exponent, you got to multiply by the base. If you decrease the exponent, you have to divide by the base. Wild. Negative exponents mean divide. What? Negative exponents mean divide. So that's what they mean, because we want to make sure that they follow the pattern. And trust me, everything works beautifully when we think of negative exponents as dividing. So what we can see, first of all, is that a to the 0 equals 1. Cool. Anything to the 0th power is just 1, because we're taking 1 and we're not multiplying by the base. So -2 to the 0, that's 1 times -2, no times. That's 1. This is 1 times 40, no times. That's 1. 2 to the 0 is 1, so this is just 2 to the 5th times 1, which is 32. And that works, by the way, because we get 2 to the 5 plus 0 using our rule from above. Same bases, exponents, add the exponents, and that just becomes 2 to the 5th. So there's one example of this rule making sense for other rules. 3 to the 0 times 3 to the 4th would be 3 to the 0 plus 4, which is just 3 to the 4th, which is 81. But also 3 to the 0 is just 1. So again, it should just be 1 times 3 to the 4th, which it is. That's 81. Okay, so anything to the 0th power is 1. I love it. It's very cool. It's not 0. No, it's 1. 0 has to do with addition again. 0 is an additive thing. 0 is not a multiplicative thing. Okay, we're dealing with multiplication and exponents, so we gotta be in the world of the ones, not the zeros, for the most part. I don't really know what I'm saying, but I think that's kind of true. Okay, finally, the indigo rule. When you have, not finally, we still got a long way to go. When you have, not that long actually. When you have a negative exponent, that means divide. Oh my goodness, this is really important. to remember. 3 to the negative 4 equals 1 over 3 to the fourth, which is 1 over 81. 4 to the negative 2, that is 1 over 4 squared. Now, 4 squared is easy. It's pretty easy for most of us. If it's not easy, that's fine, you know, but it makes sense to us, I think, for the most part. 4 times 4, that's 16. Great. 4 to the negative 2 makes 0 sense to me. What does that even what does it even mean? But 1 over 4 squared, I can understand that. That's just 1 divided by 16. So I just have to remember to rewrite my negative exponents as positive exponents and then simplify. Whoa, rewrite your negative exponents as positive exponents, then simplify. Negative exponents mean divide. 5 to the negative 1, 0 idea what that is, except for I know that it's division. So it should be 1 over 5 to the first power, which is just 1/5. 2 to the negative 3, that should be 1 over 2 cubed. And 2 cubed is just 8, so that's 1/8. Okay, so negative exponents mean divide. Okay, let's clear all this nonsense. Let's scroll down because that's something we know how to do because we're computer savvy. Let's have a sip of this Kenyan coffee, roasted by Olympia Coffee Works. Not bad. Come up with specific values for a, m, and n to show that the Violet rule a to the m over a to the n equals a to the m minus n is true. Great. You know what? Let's come up with a value for a. Let's come up with a value for m. Let's come up with a value for n. Let's say a is 3. Let's say m is, I don't know, what do you want it to be? 7? 7? 7, sure, 7. And then n could be, I don't know, 2, sure. So if we plug this into both sides, let's say we've got a to the m over a to the n. So that would be 3 to the 7th divided by 3 squared based on the numbers we chose. Now let's write that out. That's 1 times 3 times 3 times 3 times 3 times 3 times 3 times 3. Now this would, if we didn't have exponents, we have to do this every time. So don't complain that you have to do it once, because exponents are saving us a lot of work. We only have to do it this time. And then 3 squared is there. Hey, we can divide these 3's, right? 3 gone. And we just end up with 1 times 3 times 3 times 3 times 3 times 3. So there are 5 of them. That's 3 to the 5th. Interesting. Now over here on the other side, if we had a to the m minus n, that would be 3 to the 7 minus 2, which is 3 to the 5th. Ha! Look at that. Same, but different. But no, they're not. They're actually just same. Okay, so basically we've just shown with one example that this thing seems to probably be true. We haven't proved it, but it seems like it could be true. All right, let's clear that. I think we're about done here. If we scroll down here, here is for you to summarize. This is probably the most important because this is what you're going to use later on, right? When you're working through things. I'm not going to work through this, but here are all your rules. Okay. I hope this was helpful. Looking forward to practicing some exponential rules with all of you, or most of you. All right, see you later. Bye.